Hi, this is Roopa Prasad, Assistant Professor, Department of Computer Application, MITS. Okay, today we are going to discuss about the topic called Advanced Encryption Standard, that is called as AES, which is a symmetric block cipher algorithm. Okay, let's see the contents of the algorithm. So first we are going to discuss about the general structure of AES. Then we go for the transformation functions that are present in AES. Here we have a substitute byte function, then shift rows, then mix columns and add round key. And finally we discuss about the AES key expansion. So, coming to this advanced encryption standard, which we call it as AES, this AES is a symmetric block cipher. So, this AES algorithm is a symmetric block cipher, and this has been published by National Institute of Standards and Technology (NIST) in 2001. Okay, so we call this is an example of symmetric block cipher. So it comes under the category of symmetric cryptographic algorithm, and that too it is a block cipher because we are going to operate the encryption and decryption algorithm on the block of plain text. So we are calling this as a block cipher. So here the block size will be 128 bits. Here the plain text block size will be 128 bits, or we can call it as 16 bytes. That is 16 into 8, that is 128 bits. Okay, and whatever the key we are using here, it has a variation. So we can use a 16 byte key or 24 byte key or 32 byte key. So the key can be 128 bit or 192 bit or 256 bit. So we can refer here in bytes also. So because it operates on the bytes. Okay. So the key length can be varied 16, 24 or 32 bytes. So it can be 128, 192 or 256. Okay. Suppose we are using in a particular algorithm we are using 128 bit key, then we call this algorithm as a AES 128. If we are using 192, we can call it as AES 192. And if we are using 256 bit key, then we are calling it as a 256 AES 256. Then so here in AES algorithm, we have a variation in the rounds, number of rounds. In DS, we already know that in DS algorithm we have 16 rounds are there, but in AES algorithm it is variable, depends on the key length. That means, suppose if we are using 128 bit key, then AES algorithm uses 10 rounds. So if we are using 192 bit key, then it is having the 12 rounds. If we are using 256 bit key, then it is having 14 rounds. So depending on the key length, the round may also vary. Okay, in DS we have fixed rounds, that is 16 rounds are there, but in AES we may have 10 rounds, 12 rounds or 14 rounds depending on the key length. Okay, and each for each round we use a sub key that we call it as a round key, and that round key is of 128 bit. Okay, even though we use a 128 bit key or 192 bit key or 256 bit key, for each round, we are going to generate one unique 128-bit round key. So, which is calculated from the original AES key. So, the original AES key may be 128 bit, 192 bit, or 256 bit, but we are generating a unique key for each round, and the key size is 128 bit. These are the basics of AES algorithm. Then we go for the general structure of this algorithm. So here for this algorithm, what will be the input? The input will be the 128-bit plain text that has to be transformed into 128-bit cipher text. In between this, we have the algorithm. So in this algorithm, we have rounds. Okay, here we are specifying n rounds. Why? Because means the rounds may differ depending on the key size. Already said, if we have the key size is 128, we have 10 rounds. If the key size is 192, we have 12 rounds. If the key size is 256, we have 14 rounds. So depending on the key, we have the rounds. Okay, so we have n rounds are there. Before this round one, we have one more extra round that we call it as a pre-round transformation. Pre-round transformation. Upon each round, we are using a unique sub key, that is a round key. Here we call it as a round key, and this round key is of 128 bit, which is generated from the cipher key. The cipher key is of any size. From this cipher key, we are going to expand 128 bit n keys. N plus 1 keys, because we have n rounds, and for this pre-round transformation also we need one key. So that we call it as we have n plus 1 round, n plus 1 keys, n plus 1 keys that will be generated from the cipher key, and each key is of size 128 bit. Okay, so this is the input and this is the output. In order to get the output, we have to process through the algorithm. In the algorithm, we have the n rounds, and prior to this round one, we have one pre-round transformation is there. For each round, we are using a unique sub key that is called as a round key of size 128 bit, which is generated from the cipher key. Okay, so that is a general structure. Hope you understand. So, so the input for the encryption and decryption algorithm is 128-bit key. The 128-bit block, that is the plain text is of size 128-bit, and this block, and we are treating this block as a 4 by 4 square matrix. That means we are treating this as a byte, 4 by 4 bytes. Okay, so this 128-bit, that is 128-bit plain text, can be viewed as 4 by 4 square matrix of byte. Okay, so this block is copied into an array called as a state array, so which is to be modified at each stage of the encryption and the decryption. Okay, so whenever it is passing through the rounds, the state array will be modified. First, what you are going to do, you are going to convert this plain text into an array, that is a 4 by state array, that is a 4 by 4 square matrix, and this state array will be go through all the rounds in order to get the output. Whenever at the final stage, what we are going to do, we are going to transform this state, copy this state into the output matrix, that is called as an output ciphertext. And so here, for each round we have 4 transformations are there, 4 different stages, or we can call it as a 4 transformations. One is called as substitute bytes, and the one is called as shift rows, and next one is called as the mix columns, and next one is called as add round key. These are the 4 transformation that has to performed in each round. Okay, actually I said we have n plus 1 rounds. One is called as a pre-round transformation, and remaining will be the n rounds. So what happens in the both encryption and the decryption process? So it begins with the p-round. It begins with the pre-round transformation, where we are going to use a key. In the pre-round transformation, we have only one transformation, that is called as a add round key transformation. Okay, followed by 9 rounds. And all the 9 rounds we are using 4 stages. That is substitute bytes, shift rows, mix columns, and add round key, followed by the 10th round, followed by the last round of 3 stages only. Here in the last stage, in the last round, we don't have the mix columns. Okay, so what happens in each round? In each round, we have 4 transformations, or we can call it as 4 stages. The first stage is substitute bytes, and the second stage is shift rows, and the third stage is mix columns, and the fourth stage is add round key. Okay, in round 1, okay, in round 0, that is a pre-round transformation, we have only this stage is available, that is add round key stage is available. In the remaining rounds, in the remaining n minus 1 rounds, we have all the 4 stages, but in the last round, that is the nth round, we have the 3 stages only. Okay, here mixed columns is not available in the last round. That is, for example, if we are going to do 10 rounds, that is, if the key size is of 128 bit, then we have the 10 rounds, and we have one pre-round transformation. For this pre-round transformation, we are going to use only one stage, that is add round key, and in the remaining 9 rounds we have all the 4 stages, that is substitute bytes, shift rows, mix columns, and add round key. But in the 10th round we have only 3 stages. This is not present in the last stage, that is this transformation, this stage is not present in the last round, that is a mix columns is not available. Okay, so here, so the every stage makes use of the key. Every stage makes use of the key. So it begins with the add round key stage and ends with the add round stage. That is, here we have the pre-round transformation. We have seen the structure. So in the first one, what we have, pre-round transformation, there we are going to make use of the add round key stage, and at the end also we are having the add round key stage. So it starts with add round key stage and ends with add round key stage. Okay, and every round is going to make use of the key. And so this can be depicted graphically like the pictorially like this. So we have a plain text of 128 bits. This can be viewed as 16 bytes. So this will be transformed first before going to give to the initial transformation, that is a pre-round transformation. What we are going to do, this has to be converted into array, converted into matrix, sorry, converted into matrix, and this is a 4 by 4 matrix, and we call it as a state array. We call it as a state array, which is of 16 bytes, 4 by 4. 4, 4 rows and 4 columns. Totally, we have the 16 bytes that will be given for the initial transformation. That is a pre-round transformation, round 0. Upon this round 0 also, we are going to use the key that is generated from the main key. Okay. Here also, the key is of 120. Suppose the key is of 128 bit. Okay. That will be converted into a matrix of 4 by 4. Okay, from this 4 by 4 matrix, we are going to generate the sub keys, that is a round keys, which is of 128 bit. This is also represented in the form of matrix that will be applied to the initial transformation. Okay, then after the initial transformation, the output, that is a state array, that is the output of the initial transformation, is also the state array of 16 bytes that will be given for round 1. Okay, in round 1, we are having 4 transformations. Upon what are the transformations? First one is called as a substitute byte, second one is called as a shift rows, and third one is called as a mixed columns, and fourth one is called as a add round key. Okay, for this add round key transformation, we are going to use a round key which is of 16 bytes, which is represented as a matrix. Like that, we are going to continue. Okay, so in round 1, we are going to perform 4 transformations, and after completing the transformations, here we get the output. This will be called as an output state, which is of 16 bytes only. That will be given for the next round. As usual, for the next round also, we are using the round key. In the next round also, we are having the 4 transformation. Like that, it continues up to n minus 1 rounds, where we have four transformations are there. The output of this round is this n minus 1 round is given to the nth round, which is having only 3 transformations. Okay, here we don't have the mixed column transformations available in the nth round. So, and on this nth round also, we are going to apply the key. For that purpose only, what we have said, we have n rounds are there. And if we have n rounds, then we have n plus 1 keys. So, this is a final state of 16 bytes, which is arranged in 4 by 4 matrix. That has to be given as the output, which is a ciphertext. Okay, that's a flow of the algorithm. There is a flow of the AES structure, and this already we discussed. So what happens, we are going to give the plain text of 128 bits to the add round key. There is a pre-round transformation. In pre-round transformation only, we are having the add round key. Upon this add round key, we are going to use a key which is of 128 bits, and this key is viewed as 4 words. Okay, this key is viewed as 4 words of each 32 bit, that we will discuss in the key expansion. So what happens is, for 128 bit key, which is organized as 16 bytes, will be expanded in order to get 4 words. 4 words. Each word is of 32 bit. Each word is of 32 bit. So we are having word 0 to word 4, that is given for add round key. That is pre-round transformation. That is 128 bit only. That is represented in the form of 4 words. So for 10 rounds, we are going to generate 44 words. Okay, for 10 rounds, for 10 rounds, we are going to generate 44 words. Okay, each key is of size 4 words. This is a pre-round key, that is round 0, and this is round n key. Okay, so this key is generated from the main cipher key. Okay, so that is given for add round key transformation, that is pre-round transformation. Then the output is given for round 1. In this round 1, we have 4 transformations, but for last transformation, we are going to make use of the key. Okay, then the output is given for next round, like that it flows. Then the output is given for the n minus 1 round, that is the 9th round. Here we are having 4 transformations only, and after that we are going to give the output at the 10th round. Here we are having 3 transformations only. Here mixed columns transformation is not present in the 10th round. Upon in each round we are going to make use of a round key, which is represented as 4 words, word 0 to word 4, which is expanded from the main cipher key. and this is a decryption process. Same decryption process is also same. But what happens here, the input is a ciphertext and output is the plain text. Here we have to take the key in the reverse order. That means what? The last key, that is n minus 1 key, which is the word 40 to 43, will be given for the round 1. That is a pre-round. And like that it flows. It is opposite to encryption process. In the encryption process, for the pre-round transformation, we are going to use the word 0. In the same manner, word 0 to 4, that is the first round key will be used. In the same manner, here also we have to use, but the keys are inverse. The keys are inverse. The last key, the last round key is given for the first pre-round transformation, that is round 0. Then n minus 1 key will be used for round 1. Then n minus 2 key is used for round 2, like that it flows. Okay, and the round 0 is used for the 10th round, so that we are getting the plain text. That is, this is an encryption process, and this we call it as a decryption process. And now coming to the transformation function, transformation. So what is going to happen in the transformation? Okay, we have already discussed, we have the 4 transformations are there. One is substitute bytes, second one is shift rows, third one is mix columns, and fourth one is add round key. Okay, so we'll discuss about each transformation, what is going to happen in the transformation. So what is the first transformation? Substitute bytes. We can simply call it as a sub bytes. We can call it as a sub bytes. Okay, so for this sub bytes transformation, we are going to make use of a S box, that is a substitute box, which is of 16 into 16 matrix, which is a 16 into 16 matrix, that I will show diagrammatically, so that you can clearly understand. So this we call it as S box, so which is a predefined box, and this is where we are having the state array, input state array, and this is the output state array for each round. Okay, so this is an input state array which we are passing into the round. So first transformation is substitute byte transformation. Simply we can call it as sub bytes. Here we are going to make use of S box, which is of 16 by 16 matrix. 16 by 16 matrix, which is a predefined matrix. Okay, how we are going to substitute here means, so these are the 4 by 4 matrix. So this is first cell, second cell, third cell, fourth cell, like that we have row 0, row 1, row 2, row 3. Here we are having a value which is a hexadecimal. So here see this one. Okay, so how this value will be substituted means, here we are going to have the row and column. Okay, suppose here we are having 2D, the value is 2D. Okay, the first element is considered as X row, and second element is considered as Y. Okay, X and Y. For example, we are having the value 2D. 2D has to be replaced. It has to be substituted. So how we are going to substitute means, by making use of S box. We have discussed about the substitution technique, substitution. So how we are going to substitute means, so here this value, suppose think that this value is 2D. Okay, now what happens, this 2 is considered as row number and D is considered as a column number. So we have to check here. Okay, second row and D column. Second row and D column. Here we have 16 into 16 matrix. The matrix of 16 by 16. So on this intersection, we have some value. That value will be replaced. That value will be replaced. That value will be substituted. Is it clear? So what we are going to do? We are going to make use of S box, which is of 16 by 16 matrix. And these are the input array which contains a value. Suppose this cell, this particular cells contains a value of 2D, which is a hexadecimal values only, 0 to 15. So here also same thing. So the 2D. Okay, so we are going for the second row. We are going for the second row and dth column. Okay, first element is a row and second element is a column. We are going for the second row and dth column. So whatever at the intersection point, so this is X and this is Y. At the intersection point, there is a value, isn't it? That value is substituted in this place. Okay, like that we are going to substitute all the elements in the array. That we call it as a substitute byte transformation. The bytes will be substituted. Is it clear? The bytes will be substituted. Like that we are going to convert the input array into an output array after performing the substitute byte transformation. Simply we can call it as a sub bytes. Then we have another transformation that we call it as a shift row transformation. So here shift row means here we are going to perform the permutation, not the substitution. We are just changing the positions. Okay, simply we can call it the shift row. Shift row transformation can be called as shift row. Here what is going to happen means the first, these are the four rows. These are the four rows of the input array. So we have to generate the output array. Okay, so what happens? The first row is not altered. The first row is not altered. It is replaced as it is. Okay. For the second row, we are going to perform 1 byte circular left shift. 1 byte circular left shift. We are going to perform shifting. We are going to perform shifting. So how shifting is done? Left shift. We have to perform the left shift. Okay. Then what happens for the third row? We have to perform 2 byte circular left shift. And for the fourth row, we have to perform 3 byte circular left shift. That is the thing we are going to do. Okay. That's what we are going to do means we are going to shift. We are going to shift, left shift. So this easy come out. Then next one, what is 90? 90 will be in the third column. 4C will be in the second column and 6C will be in the first column. And this EC will be placed here. Circular left shift. Circular left shift. Okay. So like that we are going to perform. Like that we are going to perform the shifting. So as I told you, the first row is not altered. The first row is not altered. Second row we are going to shift 1 byte. And third row we are going to shift 2 bytes. And in fourth row we are going to perform 3 bytes shift. That is, circular left shift has to be performed. This is a simple concept. What we call it as a shift row transformation. And another one is called as another transformation is called as mixed column transformation. Mixed column transformation, simply we call it as a mixed columns. We call it as a mixed column which is going to operate on each column, So here what we are going to take means you are going to take one predefined matrix, 4 by 4 matrix, predefined 4 by 4 matrix will be taken. Okay, and every column of the input matrix is multiplied with the 4 by 4 matrix, so that we are going to generate one column. Okay, so what is this column? What is the size of this one column? We are having 4 rows and one column. 4 into 1 multiplied with 4 into 4. 4 by 1 matrix is multiplied by 4 by 4 matrix. Obviously, we get 4 by 1 only. 4 by 1. That will be substituted here. This matrix, this column is multiplied with this matrix and we get the column, output column. That output column will be placed here. Like that, we are going to mix all the columns. This we call it as a mixed column transformation, which is not present in the last round, that is the nth round. In the nth round, we don't have the mixed column transformation. And finally coming, the fourth transformation is add round key transformation. So in this transformation only, we are going to make use of the key. We are going to make use of the round key. Okay. So what happens, how this is going to happen means, this is the input matrix, that is a 4 by 4 matrix, and this is the key. Okay. Now what we said, the key is represented as 4 words. The key is represented as 4 words, each of 32 bits. Here we are going to perform XOR operation. The column 1 is XORed with column 1, that is a word 1. Okay, word 1 of the round key. Then we are getting this one. Clear? This column is added, XORed with next word, so that we are getting this column. Okay, like that we are going to perform the transformation. Column-wise operation is performed between the 4 bytes of state column and 1 word of the round key. Is it clear? 4 bytes of state column. This is a 4 bytes of state column is XORed with 1 word of the round key. The round key is of 4 words. Each word is of 32 bit. And this is viewed as a byte level operation. Okay, this is the fourth transformation that we call it as a add round key transformation. So here we are going to make use of 128-bit key that is given as 4 words. each word is of 32 bit. Here we are going to perform the XOR operation between the each column of the input state array with each word, so that we are getting the corresponding column of the output matrix. These are the four transformations that we will see here. So what happens at the beginning, state matrix at the beginning of a round. So that 128-bit plain text will be represented as a 4 by 4 matrix that is given for each round. Okay, we see what happens in each round. So we are having four transformations are there. So sub-bytes transformation. So it is going to make use of the S box. It is going to make use of the S box so that it generates one output matrix which is given for shift rows. Here nothing will be done. Here rows will be shifted. That is simple permutation is done, and this is output matrix which will be given for the next transformation that is called as a mixed columns transformation, where we are going to make use of mixed columns matrix. So that is each column is multiplied with each column of the state array in order to generate the output state matrix. Then that will be given for the fourth transformation that we call it as add round key, which is going to make use of the round key. So it generates a state matrix at the end of each round. This matrix will be given for the next round, and it follows. But you have to remember for round 0, that is the pre-round transformation, we have only add round key transformation is there. And in the nth round, that is in the 10th round or in the last round, we have only 3 transformations are there. This mixed columns is not available. We have only sub-bytes, shift rows and add round key transformation. Next, we discuss about the key expansion. Okay, so here in AES key, we have a variable keys are there. So we can make use of 128-bit or 192-bit or 256-bit keys are there. So whatever the may the key size, it is going to generate 128-bit subkey. That is a round key. Okay, that means that is represented in 44 words. For example, we are taking 10 rounds. Okay, 10 rounds of AES. So in this 10 rounds, it is going to generate 44 words. It is going to generate 44 words. Okay. How this is going to generate means, how it is going to expand means, that we will explain. Okay. This is a key expansion. So the key is represented as 16 bytes, 4 by 4. So from this one, from the first column, you are going to get word 0. So every word is a 32-bit. Okay. Though for the second word, word 1, we have this column, word 2, this column, and word 3, this column. This is sufficient for pre-round transformation, 3-round transformation. So now you have to generate remaining words. You have to generate 44 words. Okay, we got only 4 words are there. So we have to generate remaining 40 words has to be generated. How these are generated means, by we are using one function. We are using one function that is called as a G function. So for this function, this word is given as an input. Okay. So what happens? So here we are going to have the permutation. Just we are going to permutate the bytes. 4 bytes are there. So these 4 bytes are interchanged, transposed. They are permutated and they are given for the substitute bytes. That is S box is there. So that it generates a new bytes. Okay. That new bytes will be XORed with a constant. Will be XORed with a constant in order to generate the new word. Okay, so this new word is XORed with the previous word. This new word is XORed with the previous word to generate the word 4. Okay, this word 4 is XORed with word 1 to generate word 5. This word 5 is XORed with word 3 to generate word 6. This word 6 is XORed with word 3 in order to generate word 7. Okay, like that it continues. Like that it continues. Now here what happens is W7 is given to the G function where it is going to generate new word. That new word is XORed with previous word in order to get the next word. Okay, like that it follows. Like that it follows. Clear? Is it clear? This transformation, this you need to understand. The key is also represented as 4 by 4. So from this 4 by 4 matrix, we are going to generate only 4 words. So next words, how the next words can be generated? By using a function called as a G function. G function flows like this. So we are generating the new word. That new word is XORed with W0 in order to get W4. This W4 is XORed with W1 in order to get W5. This W5 is XORed with W2 in order to get W6, and word 6 is XORed with word 3 in order to get word 7. Like that it follows. Okay, hope you understand. So these are the references from which I have made these slides. Okay, so this AES, one more thing you have to remember, this AES does not follow the FISA structure. DS follows the FISA structure, but AES does not follow the FISA structure. So what is our plain text block? 128 bit. 128 bit will be transformed into 128 bit cipher text. So that is the AES algorithm. Hope you all understand. And if you have any queries, you can leave your queries here. Thank you.